First, we'll look at an implementation using an array. Okay. And remember, we're going to want to analyze our data structure and see what kind of behaviors it needs, as well as what kind of backing behaviors are good and bad. So we're going to try to make this be as efficient, both memory-wise and code-wise, execution-wise as possible. So remember, stacks only add and remove from one end. We're only touching the top. Everything else is static. So if we're using an array, what operations do we want to avoid using? And the answer is we want to avoid adding or removing from an arbitrary index in the array. If we're adding and removing from an index that is just, could be any index, that could mean that any elements past that index are going to have to be shifted. And that's a big O of N operation, so that's slow. Conversely, what operations do we want to take advantage of? Well, access and overwrite are real fast, right? That's just indexing. So if we can just do some quick math, access an index, overwrite that data, and then keep going, we're good. So the goal is, if we know which slots are unused, we can get to it quick and overwrite it. It's not going to be a big deal. Okay, what does this mean for our design? Step one, we're using an array. So anytime you're using an array, you have to create an array that is larger than the space that we need, at least in the beginning. Ideally, what you want to do is make the array as large as you will ever need, but that might not be doable. If you know how many elements are going to be in this thing maximum, you're good. If not, just make it an arbitrary, make it an appropriately large initial, and then we'll deal with resizes as we go. And then what we can do is left justify our data and define index 0 as the bottom. Because we're never going to do operations at the bottom. We'll only do operations at the top. If we're writing to an unused slot, it's big O of 1. Well, look at this. We got 7 elements in this array. If we write to index 7, we got our new element. Now all we have to do is increment a variable count, right? So now our length becomes 8, and we're good. Hey, if we want to pop, all we got to do is grab the thing at the index of len -1, the number of elements that you have in your stack -1, grab that, nuke the data there, subtract 1 from the size, and return that data, and you're good. So that's it, right? The top of our stack should be the end of the currently used portion. Pushing onto a stack means writing to the first slot past the used portion of the array, and then incrementing a count variable. Popping means saving that element, overwriting the slot, decrementing your count variable, returning that saved element. And peeking is just accessing the element at len -1. Well, what's the runtime of these operations? Well, writing to a slot is big O of 1, and incrementing a variable is big O of 1. Saving an element in a variable is big O of 1, overwriting is big O of 1, decrementing is big O of 1, returning is big O of 1, accessing is big O of 1. All of these are big O of 1. And you're going to see that's going to be a consistency. We're going to aim for this across the board. Okay. There are some downsides, though, and they're mostly memory-based. Mostly. Number one, the memory representation is contiguous, very tightly aligned. It uses less memory, but that also means that you have to have that memory available, right? And there's the risk that you didn't make the array big enough at the beginning. So then you might run into the performance issue, right? So you need a big chunk of memory because it's contiguous. And if you don't have enough memory, if you have to add, if you have to, expand your array, you're going to have to go through the process of resizing the array. And I hate resizing my arrays, but we can do it. And so I'm just going to walk you through an implementation. It is available on Canvas, but we can do an array stack. Now, some things, okay? Step one, we're importing our stack interface, right? And then we're going to import from exceptions this empty stack exception. And the first thing we're going to do is we're going to implement our our stack interface. Okay, and then we're going to go through and notice, right? These comments are largely the same. I add a little more detail here, right? Creates a new stack by creating a backing array at our default capacity and saying the length is 0. So we are going to be technically using a dynamic array, but we're going to treat it like a standard array. Now, what I have here, right, 10, is the same as what I had a moment ago. This array stack.default capacity. Why am I doing it this way? Well, one, it's generally better practice, right? You have this all capitalized underscore here is defined up here. And this is typically representative of a variable that is considered a constant, which means it's not going to change during the execution of your code. Right? It's something that will only change at the beginning. So, hey, I've changed my default capacity to 100. So when I start running it, it's a different value. Why would this be useful? One thing I want to point out is that this is useful because it allows you to have a variable that counts as that sort of counts as a sort of parameter. It's not a parameter as in this kind of parameter, but it's a rule that governs how your code runs, and it's stored in a variable. So instead of having it times 10, and then every time in your code you see a 10, you have to decide, oh crap, is that based on default capacity or is it just happened to be 10? You can just have this represent what it is, okay? Another thing is that this is almost universal, the way this works. This all capitalized, separated by underscores. I have never seen a high-level programming language where this means anything other than a constant. So it's good to know when you see this in code, you should think constant always. Okay. And an example I've been using that people can kind of get their mind around is imagine that there's a video game that's created that comes out and it allows 8-person multiplayer, right? You might have a default capacity, right? Instead of default capacity, you might have something called like max players, 8. And that's going to be used throughout your code, right? When you're adding players, hey, how many players do we have? 8. Okay. When you're setting up the screen, how many players do we have? 8. Okay, great. Right. But you might have plans in the future to expand the number of players to 20 or to, 100 eventually, right? Well, that's great. Now all I have to do is change this one variable, and all the places that reference max players, it's automatically updated. Right? So I'm going to have to change my code to be able to enable that many players. But once I've got my code changed, I don't have to do anything else other than change that variable, and it should automatically work. So that's the concept behind this. So that's why I wanted to show you that. So we create our array to a default size, and we set our length to 0. Remember, the length is the number of elements in our stack, not the number of slots in the array behind the scenes. Okay. So when we push, we're just going to write to the last slot, except there's a problem. What if our array is full? What if we don't have any more space in our stack? So that's what we do here. Hey, if the number of elements in our stack equals the number of slots in our array, then that means that every slot is full. I can't add to this stack without breaking it. So I'm going to have to resize it. And I'm just going to double the length of my data. Right? So if I've got 10, I'm going to go to 20. If I've got 20, I'm going to go to 40. Right? Once that gets done, and we'll see how that works in a moment. Once that gets done, whatever the position that we're supposed to write to equals our new element. By the way, if this doesn't have to get done, this still is true. Right? Once we have an array of the size that is appropriate, we write to the slot and we increment our length. And that's it. That's all we have to do. And if we come down here, we can see resize backing array to our new size. The first thing we do is we grab our data and we store it, right? We want to keep a reference. So now we get a copy of our old data as well as the data in our array. Well, that's gone now. We just created a new array of the appropriate size and overwrote our objects data, but we still have our old data, right? We still have that reference. And what we do is we say, hey, for every element in our old data, right? That's length, right? For every element in our stack, we're just going to copy from the old data to our new data, and we're done. Now we've got a new array. If it was 10 and now it's 20, right? We're going to have created a new array of size 20, but we're going to have copied 10 elements. So we're going to have 10 more elements at the end that are blank. Great. So we'll go up instead of down. This will be easier. Our length, the number of elements in our well, that says queue, it should be stack. Right? The number of elements in our stack, well, that's this variable, whatever it is, right? That's great. It's easy, right? Every time we push, we add one. Every time we pop, we subtract one. So that's all we have to do. Peak, we just have to get the data at len minus 1. So we can say, hey, return self._data, the length of my self minus 1, whatever the number of elements that I have in my stack minus 1. If I've got 9 elements, I want to go to index 8. If I've got 1 element, I want to go to index 0. But I only do that if my length is greater than 0. If I've got stuff in my stack. If I don't have stuff in my stack, I'm going to raise an exception. I'm going to say, hey, there's no elements in my stack. So that's fine. And then we can come up to pop, and we could do the same thing if we wanted to, or we could just let peek do it. Hey, look, we go into pop. We want to get the first element that we're going to get. Hey, that does that. If we have elements, return it. If not, raise an exception. This will raise the exception. It will be fine. So now that we have that element saved, we can nuke the data that we just read, set it to none. We can decrement our lengths, and we can return our saved element. And we can test it if we want. S equals array stack, right? And we can see a._data, right? We can't touch. Did I do that wrong? What do I call it? Oh, because it's not A, it's S. Duh. Here. S._data. And we can see the backing array. Now, should we do this, most of the time? No, but we're testing it. We want to make sure everything works. So we need to run the car while the hood's open. So let's do that. S.push 1. Hey, look, it works. Len of S. Hey, look, it works. S.pop. S.peak. Right? And you want to test all these things. You want to make sure that's working. What's the other thing we need to test? Well, let's make our array, let's make sure that we have to do a resize. So we'll say for I in range, let's make it 15. All right. So that'll be 0 through 14. S.push, and we'll push I plus 100. So we'll get 100 through 114, hopefully. And now we can look at our data, and we should get a larger array. It should not be this big. Hey, look, we got a resize with the right data. Cool. And let's hey, let's do some fun things. Let's play around. Let's for I in range 15. Let's go even further, right? We've got, what did we do? We did for I in range 15. So let's do 17. Okay. And what we'll do is we'll try, and you can see how this would work in real life. Try print s.pop, right? And then we'll say except empty stack exception. And we'll say, we'll just print, oops, cell empty, right? And then we'll say except, and this will be a catch-all, and we'll print double oops. I don't know what happened. And hopefully we'll never see this, right? And else we'll print was okay. And then finally, we'll print iteration completed, right? So one iteration completed, we'll put. Okay. So what this is going to do is it's going to loop 17 times, no matter what. Now, what we should see are 114 through 100 printed, along with, so it should print 114 was okay, one iteration completed. 113 was okay, one iteration completed. Until we get past 100, then we should see two iterations of oops, so empty, one iteration completed. So let's see what happens. 114 was okay, one iteration completed. 113 was okay, all the way down through. And then we can see, oops, so empty, one iteration completed. Oops, so empty, one iteration completed. And if we check our backing data structure, right, everything's back to normal. Everything's back to empty. So this is how you can test things, right, as you're building them, is to just try what you think should happen and then make sure it happened. So this is it. This is an implementation of a stack using an array.